This is the second lecture in the series on using ultrasonic waves. We shall look into the A, P, M, and Doppler modes of ultrasound imaging operation. We will study how the Doppler effect is used to determine the blood flow's velocity. Now let's see modes of operation for ultrasonic imaging. There are four modes of operation in ultrasonic imaging. A, P, M, and Doppler modes operation. The transducer is fixed at a certain position in the A mode of operation. The transducer is fixed at a certain position. The backscattered sounds refracted from various tissue boundaries are detected by the transducer, and the images are created utilizing the signal intensities, various amplitudes of the sound wave. So transducer is fixed at a certain position, and we emit the ultrasounds, and we can detect the backscattered ultrasound waves at various tissue boundaries, here and here. Okay, so we can get the signal intensities, the diffractance, as function of depths. So different depths. So this kind of signal can be obtained using A mode of operation. The amplitude that is used for image formation in this mode of operation gives A mode its name. So A stands for amplitudes. The figure depicts the schematic diagram for the A mode operation. So in the A mode of operation, we can have the signal as a function of the depths of the human body, from skin. This figure depicts an example of A mode of operation. This is done to see if there is a brain tumor. A transducer sends an ultrasonic pulse to the brain through the reason near the ear, which is not blocked by the skeleton. So at this position, transducer emit the ultrasound wave. The ultrasonic wave is then refracted back to the transducer by the tissue boundaries. Okay. The interbrain, this is interbrain region. The interbrain and the endobrain boundaries here. This endobrain boundaries, and there is interbrain boundary here, where the primary backscattered signals come from. Okay, so we can have the backscatter signal from interbrain boundary, and backscatter signal from endobrain boundary here. Okay. These echo signals are denoted by 1 and 2 in the figure. So this one is a signal refracted from the interbrain boundary. 2 represents a signal refracted from endobrain boundary. If there is no tumor in the brain, the time it takes for the backscattered signal 2 to be detected is twice as long as it takes for backscattered signal 1, because for signal 2 the distance, traveling distance, is twice of that 1. So if there's no brain here, no some tumor, brain tumor here, the time taken by backscatter signal 2 is twice that by the signal 1, okay, because the traveling distance is twice. As a result, the distance d1 is d1, and d2 in the figure should be the same. Okay. However, if a tumor is present in the left half of the brain, for example here, okay, the speed of sound passing through the tumor is larger than the speed of sound passing through the normal tissue. So the speed of sound passing through the brain tumor is larger than the speed passing through the normal tissue. So as a result, signal 2's detection time is not exactly twice that of the signal 1. So in this way, as a result, the signal in the lower part of the figure will be detected. Okay, so time for this signal to the detector is shorter, because the speed of sound passing through the tumor is faster. So ultrasound imaging's A mode of operation can be used to detect tumors in the brain. The M mode of operation is depicted schematically in the figure. The backscattered signals are monitored as function of time, with a transducer fixed in position. So transducer is fixed at a certain position, and the backscattered signal are obtained as function of time. So A mode operation, we also fixed the transducer position, but we measured the backscattered signal as a function of the depth of the body from the skin. But in the M mode operation, we measure the backscatter signal as function of time. So we fixed a certain boundary. Okay, so we want to measure some certain boundary, and the motion of this boundary can be measured by using this M mode operation. It is possible to see the time variation of specific tissue boundary in this method. As a result, M mode is frequently employed to monitor the motion of heart valve of time. So if we will focus on certain tissue boundary and observe the tissue boundaries motion as a function of time. So that is the difference from the A mode operation. So A mode operation, we measure the signal intensity as a function of the depth from the skin. But in the M mode operation, we fix a certain tissue boundary, and we can observe the motion of this tissue boundary as a function of time. So there is difference between A mode and M mode operation. The figure is a schematic diagram for B mode operation. The transducer scans. So in this mode, transducer is moving. So transducer scans the ultrasonic wave across the specific slice of the body. So we can observe some specific slice of the body by scanning the body. In this case, we move the transducer. The image is created using the brightness, so intensity, of the backscatter sound waves. So the brightness that is used for image formation is the origin of this mode's name. So we call P brightness. So P mode of operation. Ultrasound imaging is the most common use for this mode of operation. Other modes of operation such as A and M modes are actually auxiliary to the B mode. Okay. The Doppler mode of operation is frequently employed to detect broad speed. When there is a relative movement between the observer and the sound source, the observer detects a sound wave with a frequency different from original frequency, according to the Doppler effect. The figure shows a schematic diagram for determining the broad speed using the Doppler effect. This is blood is flowing in this direction. Ultrasound waves are continuously sent to the inside of the body. The ultrasonic waves are scattered by red blood cells and blood flowing. The backscattered ultrasound reflected from the red blood cells is then detected by the transducer. The frequencies of the ultrasound wave sent to the body and the ultrasound wave reflected from the red blood cells in the vein are different. Okay. The beat, which is caused by superposition of these two ultrasonic waves of different frequencies, is detected by the transducer. The beat frequency detected by the transducer is used to determine the blood speed in the veins. So from the transducer, ultrasound wave is continuously sent to the body, then this ultrasound is reflected from the red blood cell in the vein. Okay. Due to Doppler effect, the frequency sent to the body and frequency backscattered from the red blood cell are slightly different. So we can observe some bit frequency, delta F. Using this bit frequency, we can determine the speed of blood flow. So there is the Doppler mode of operation. Let's calculate the frequency of ultrasound reflected by red blood cells in the vein. To find this frequency, we will take two steps. The first step is to determine the frequency of ultrasound detected by the observer at the blood cell. This frequency's ultrasound is reflected back to the transducer. So we have to first determine the frequency of ultrasound at the blood cell. Okay. The next step is to determine the frequency of the ultrasound wave detected by transducer. So this ultrasound wave is reflected from the red blood cell. So first step, we have to determine the frequency of the ultrasound observed at the site of the red cell, and then this frequency is backscattered to the transducer. Then we can determine the ultrasound wave detected by the transducer. Okay. Red blood cells are moving towards the transducer at speed of v sine theta, since blood flow at speed v in the vein, which makes angle of theta relative to the horizontal plane as shown in the figure. So in the vein, the blood is flowing in this direction, and the speed of blood is v, and the red blood cell is also moving in this direction. So this red blood cell, the velocity component to the transducer is v sine theta. So this blood cell is approaching to the transducer with the speed of v sine theta. So as a result of the Doppler effect, the frequency of the ultrasound observed on the red blood cell is given as this equation. Since this blood cell, this observer, moves towards the wave source, the transducer, so we have to add this speed here. Here C is the sound wave in the human body. So now we determine the frequency of ultrasound observed at the site of the red blood cell, this equation. And this frequency of the ultrasound is reflected to the transducer. Okay, so the red blood cell then reflects the sound waves back to the transducer, which the transducer detects. Okay? Since this sound source, in this case red blood cell, so sound waves is refracted to the transducer, and this behaves as a source now, and the detector as transducer is at stationary, but in this case the source is moving toward the transducer observer. So since this sound source, red blood cell, moves towards the transducer observer, the frequency of the refracted ultrasound observed by the transducer is expressed as this equation. Now, the source is moving toward the observer, so we have to subtract v sin theta in the denominator, and Fv is already obtained, so we can put here. Then finally we have the this frequency, which is observed by the transducer. So this is frequency observed by transducer, which is the reflected ultrasound from the blood cell. And here Fo is the frequency of the ultrasound from the transducer. So to determine the blood speed, the bit frequency between the instant wave, which is F0, and the refracted wave from the red blood cell, this one. So bit frequency can be obtained by subtracting two frequencies. So bit frequency is the difference between two frequencies. So as a result, the transducer detects two ultrasound waves of frequencies F0 and F prime, and transducer's observed bit frequency is given as the difference between two frequencies. Okay. The speeds of sound and the blood flow are represented by C and B, respectively, and we use the fact that the speed of sound is substantially faster than the blood speed. So in the last step here, speed of sound in the human body is about 1540 meters per second, but blood flow is at most 30 meters per second. So the sound speed is much larger than the blood speed. So in this case, we can eliminate this in the denominator. So we can have finally the bit frequency given by this equation. Okay. As a result, by detecting the bit frequency delta F, we can determine the speed of blood flow V. So if we measure this bit frequency by transducer, we can determine the speed of blood flow. Okay. The carotid arteries are blood vessels that supply blood to the brain, face, and the neck. So that is carotid artery from the heart, and this carotid artery through the carotid artery. The blood is fed to the brain and face and neck. So there is important arteries. Carotid artery disease occurs when plaque builds up in the carotid arteries over time. So there's some plaque is formed in the arteries. So this may limit or block blood flow to the brain, causing a stroke. This can be checked by measuring the increased blood flow at the clogged carotid arteries using the ultrasonic Doppler effect. So plaque is formed at the wall of the arteries. So blood flow, the speed of blood flow is very fast at this position. So we can measure the speed of the blood flow. Then we can this kind of signal. So we can see abrupt increase of speed at a certain position. That means that there is some plaque formed at the wall of the arteries. So in this way, we can diagnose the disease of carotid artery by using this Doppler mode of operation of the ultrasonic sound. This device shows the fetus baby ultrasound heartbeat monitor. Doppler mode is also used to monitor the heartbeat of fetus. The heart's boundary moves away from the transducer when the fetus's heart contracts. As a result, the transducer detects ultrasound at a lower frequency than ultrasound sent. Okay? Because the boundary is moving away from the source, so we can detect lower frequency. On the other hand, when the fetus heart expands, the heart boundary moves closer to the transducer, causing the transducer to detect the frequency of ultrasound that is higher than the transmitted ultrasound. So heart is expanding. When heart is expanding, then the heart boundary is approaching to the transducer. So we can measure higher frequency due to Doppler effect. So as a result, fetus's heartbeat is determined by the frequency difference between the contraction and the expansion of the heart. So in this way, we can measure the heartbeat of the fetus. One more time. When heart is contracted, then that means that the heart boundary is moving away from the detector. So we can measure the frequency of the ultrasound wave is lower than the sent ultrasound. On the other hand, if the heart is expanding, That means the hot boundary is approaching to the transducer, so we can measure higher frequency of the sound due to the Doppler effect. So the difference between two frequencies, we can give those number gives the heartbeat of the fetus. So in this way, using Doppler mode of operation, we can measure the heartbeat of the fetus. We can also measure the speed of flow in the pipe. The ultrasonic waves in the fluid are refracted by impurities or air bubbles, and the bit is created by the superposition of refracted and transmitted ultrasonic waves. We can determine the fluid speed by detecting the bit frequency. Impurities and air bubbles with a diameter of approximately 30 micrometer can cause the Doppler effect. If the number of impurities or air bubbles in the fluid is greater than roughly 25 ppm, Doppler detection is achievable. As seen in the figure, the ultrasound is instant on the fluid at the angle of theta to the flow direction. So ultrasound is sent to this direction. Then this ultrasound is refracted from the impurities or air bubble to this direction, backscatter direction. Then we can have bit frequency. We already discussed in the previous slide for bit frequency. So by observing the ultrasound bit frequency caused by impurities or air bubbles in the flowing fluid, the flow speed can be determined. The ultrasound wave frequency at impurity site is expressed as, we already discussed this as before. Here, at the impurity site, the impurities are moving in this direction, and the component of speed to the transducer is v cosine theta, right? So this direction. So impurity is moving in this direction, and we can have the speed of impurities to the transducer is v cosine theta, right? So observer is moving toward the transducer, so we have to add v cosine theta here in the denominator. Okay. The ultrasound at this frequency moves back to the transducer where it is detected. When we discussed this frequency, I said at this side the denominator. So not this denominator is right, but I remember I said this side is numerator, not numerator. I correct that. It's denominator. This is numerator, right? The impurity sound source moves at the speed of v cosine theta towards the transducer. As a result, the frequency detected by transducer, in this case, transducer is observer and the impurity is source of the ultrasound wave or frequency, this frequency. So in this case, a source is moving toward to the observer, so we have to subtract speed in the numerator, right? Not, this is the numerator and this numerator. Okay, so we put this f of b here, then we obtain this frequency. So this frequency of the transducer is the frequency reflected from the impurities, right? So as a result, the bit frequency is written as a difference between two frequencies, and we can have final result. So in the last step, we use the fact that the sound speed is substantially faster than the impurities, so we drop this term in the numerator. Okay. The fluid speed is calculated as follows. So this, so if we determine bit frequency, this bit frequency, right? Bit frequency, we can determine the flow speed. Okay. When impurity particles or gas bubbles in the flowing liquid reflects an ultrasonic signal. One more time. When impurity particles or gas bubbles in the flowing fluid reflect an ultrasonic signal, the frequency of the signal shifts. Okay. This frequency shift is used in flow meters since it is directly proportional to liquid flow rate. Okay. So flow shift means FP is bit frequency. So if we determine bit frequency, we can obtain the speed of flowing fluid. Now let's see the other applications of ultrasound waves. The ultrasound wave can be used in two different ways. The firstly, an object is detected using an ultrasound wave. The transducer emits an ultrasound, and the same transducer detects the ultrasound reflected from the object surface. The distance to the object is then calculated using the time it takes for the ultrasound to complete the round trip. Okay. This principle is used by bats and dolphins to detect the object ahead of them. This principle is also employed in ultrasonic imaging, submarine navigation, fish finders, and automobile rear sensors. Okay. Second, ultrasound energy is employed in a variety of applications, including ultrasonic cleaners, ultrasonic cutters, and ultrasonic medical equipments. So this figure shows fish finder, rear sensors for cars. This one, ultrasonic cleaners, ultrasonic cutter, it's not here, and ultrasonic medical equipment. if we use this equipment, we can destroy or we can scatter the stones in the kidney, and the scattered small stones can be out of body via the urine. So in this equipment is used to break the stones in the human body, and then using the ultrasonic energy, the stones is shattered into very small parts, small particles, and those particles can be expelled from our body via urine system. And this slide also shows some example of ultrasonic equipments. This is ultrasonic skincare, ultrasonic cleaner for eyeglasses, ultrasonic welder for plastic. It's very hard to weld the plastic because plastic is the melting temperature is very low, so it is very hard to melt two plastics together. But if you use the ultrasonic, then you can easily weld the two plastics together. And this shows the ultrasonic kidney stone crusher. And this is ultrasonic rear detector for cars. Also, we investigated the applications of ultrasonic waves, and we focused mainly on the medical applications of ultrasonic sound.